So turning to, which one did I want to do? On today's homework, I believe. Actually, I did want to go. I wanted to go over two of the problems on the homework that I just handed back. Okay, now the first one had to do. The first problem is number 29 that I'd like to review with you now. It's a simple Atwood machine with a big heavy weight hanging on one end, great big mass, M2, I guess it's called in the problem, and a guy hanging off the other end. He's going to climb up the rope. And how does he climb up the rope? He's taking in rope, right? So, and the question is, now, if he climbs at a steady rate, can he lift the weight? First supposition is that he weighs less than the weight that's on the floor. Because if he weighed more, he wouldn't have to do anything. Right? He could just start pulling and it would go up. If he weighs less than the other weight, though, is there any way for him to lift it? Now, if he's pulling on the rope at a steady rate, if he moves up off the floor at a steady speed, can he lift that rope? Can he lift that weight? No. Why not? Let's analyze the forces in that case. Okay, let's analyze the forces that are acting on him and the force that is acting on this block. So, if the block is not accelerating and he is not accelerating, so let's look at his case. M1A1 is T minus M1G, and in this case I'm marking the height of each object from the floor. Okay, so the direction of up is positive. So M1A1 is T minus M1G. If that acceleration is 0, if he's moving at steady speed, then the tension is equal, right? There's something wrong. What's going on here? M2A2 is T minus M2G. If that acceleration is also 0, right? T equals M2G. What's going on here? What is the tension in the rope? If he's just pulling up, he's not accelerating. Neither is the mass accelerating.
And they both must weigh the same.
Sorry?
And they both have the same mass.
They don't have the same mass.
Well,
right? Yeah, that would be the conclusion, right? But they don't have the same mass, right? Something is going on here, and it's because of remember, we dropped the assumption of the rope having fixed length. The rope is no longer having fixed length. The rope is changing length. So we no longer can use that. So what we're missing here, that's what we're missing from this as well, is the normal force of the floor. The block is resting on the floor, and so what we need here, in addition to this, is the normal force. And then the tension in the rope is not equal to, doesn't have that discrepancy. Rather, it tells us that the normal force is equal to M2 minus M1G, right? Which is correct. We understand that to be true. The normal force is the difference in the weights. Okay, but there's no acceleration. He's not able to lift the block off the floor. So instead of having steady speed, he has to accelerate. The man must accelerate. And then let's study the situation in that case. Okay, now, in this case, if he accelerates, then the tension in the rope is greater than his weight. That's what accelerates him, because he's pulling down on the rope is pulling up on him. So that gives a net force upward for him. So he accelerates. And in that case, the tension is going to be greater than his weight. This is going to be greater than 0. If he's barely pulling fast enough, that the block is almost to lift off the floor. In other words, that the normal force has gone to 0. Then there's no normal force in this equation here, in the second equation for the second body. And in fact, its acceleration is 0. And so the tension is equal to the weight of the heavier body. And then we find out that the acceleration has to be m2 minus m1g divided by m1. So he has to accelerate he has to accelerate at that value, which means that he's got to be pulling faster and faster and faster. Right? He can't simply pull at a steady rate. He's got to be pulling faster and faster in time. He's accelerating. The only way he can accelerate is to climb faster up the rope. And that produces more tension in the rope, which is then what lifts the weight off the floor. Now, some of you started by writing down these equations from the book on the Atwood machine. The book writes down these two equations and adds a third equation. Why does this not apply? It's not fixed length, right? That third condition there came from having fixed length between the two weights. But the two weights, there's no longer a fixed length of rope between the two weights because either you're climbing or you're accelerating. Either way, you're shortening the rope. And so that condition does not apply in this problem. And if you try to apply it, you'll get the answer that doesn't work. Okay, number 33. Is two blocks connected. It's like a combination of the Atwood machine. Let me do this in black. It's like a combination of the Atwood machine and a ramp. One mass rests on a ramp and is connected by a pulley to another weight with another mass which just hangs. And this is M1 and M2. And you're going to look at the condition, under what condition, in other words, how could I adjust that angle theta to establish equilibrium? Now, what does equilibrium mean? No acceleration. Does it mean it's not moving? No. They could be moving. It's just they're not accelerating. It means if you put them at rest, they will stay at rest because there's no acceleration. So, but that's easy to confuse. Equilibrium does not mean they're at rest, and being at rest temporarily, instantaneously, does not mean that they're at equilibrium. Right? Those two things are different. So keep that in mind. Okay. Now, what I was missing in these was just a simple force diagram. So I'm going to just emphasize that I want to see force diagrams here. There's a tension, there's a normal force, there's gravity, and that's what I want to see for one of them. I want to see the other one. We're going to be doing progressively more complicated force diagrams. I want them always. In problems like this, that should be the first step. Draw a force diagram. And don't resolve the forces onto a coordinate system yet because you haven't defined a coordinate system. I just want to know that you know that there are 3 forces acting on that block on the ramp. Now, some people put friction in, which is fine. It didn't really say whether or not to consider friction. So I realized after I graded a couple of them that it doesn't say. And so it's fine if you put friction in. So suppose that this, but you have to specify whether it's moving or not. So the general presumption seemed to be that it was moving up and that there was kinetic friction. Okay, so if it's moving up and there's kinetic friction, which way is the friction, the force of friction? So there would be a fourth force downward like this if it's moving up, because it opposes the motion. So if you did that, I caught on finally that people were doing that. That's fine. But it should show up in your force diagram. There should be 4 forces present in the force diagram, right? So this will help avoid confusion because if you do this early at the beginning of the problem, you'll force yourself to figure out what are the forces that are present. And remember, impetus is not a force, and a force is not impetus. They're not the same thing, right? So I'm looking for forces. Okay. Any questions about those two problems? I'm asking, I think, most people to redo those problems. So study the solution, put it aside, try it again. Okay, so let's look at the homework for today, Chapter 5, number 12. The question had to do with the nature of kinetic energy, as I recall. Let me see, remember. Describe in what sense energy is not a simple property of a body. So I won't go through the answer here. We talked about it a little bit. What is the basic property of a body that is related to locomotion? It's impetus. And the measure of that is momentum, which is a vector in the sense that it has both intensity and direction. Kinetic energy is another measure of kinetic activity, but it is not a simple property of the body like impetus is. It's a measure. And so it's as a measure of the momentum, it's not a simple property of the body like momentum is not a simple property of the body. It's a measure of the property of the body. Okay? All right, so and the other thing to emphasize about kinetic energy is it's not a substance. It doesn't flow, neither is energy, generally speaking. It doesn't flow from one body to another. Like a substance might be seen to flow like water flowing from one place to another. Kinetic energy is not like that. It's related to a property of the body. Okay. Let's see. What else I wanted to do? Yes, sir. Yes, sir.
Can we do 5C?
5C on the worksheet? On the
worksheet.
Is it a worksheet or is it from the book? Okay. Yeah. Okay. So, what does doubling the intensity of the impetus do to the kinetic energy? Keeping then the mass fixed, right?
Well, how do we know the mass is fixed?
Okay. So I think they're implying that there are things that you could do to it. In one case, you double the speed while keeping the mass fixed. That's A. Doubling the mass while keeping the velocity fixed. Or I suppose you're saying you could keep the impetus, the momentum fixed, I guess.
When it says doubling momentum, you could double mass, and that would double momentum. And that would not quadruple kinetic energy.
I got you. Doubling the intensity of the impetus. I would take that to mean I can understand the confusion, I guess. I take that to mean doubling the momentum and not the mass.
It's just the same as A. It's just doubling velocity.
Right. Correct.
I mean, it's the same result.
Same result.
But it's the same thing. If you're doubling momentum but keeping mass the same, then you have to be doubling velocity.
Correct.
So how do I tell from reading that it means doubling velocity? Just use mass.
It doesn't mean doubling velocity because velocity is not a property of the body. It's an effect. Right? They're not exactly the same thing. Momentum and impetus are not the same as velocity. So it may be that the result comes out the same. You're quadrupling the kinetic energy. But it's not the same thing to say you double the speed or you're doubling the momentum because they're not exactly the same thing. They're proportional.
Well, momentum is mass times velocity.
No, momentum is a measure of the impetus. You see, that's the distinction. The momentum is a measure of the cause, and the velocity is the effect, the measure of the intensity of the effect. So you may be the same in effect. The kinetic energy in effect quadruples, but it doesn't mean that what you've done is precisely the same thing. You're increasing the impetus. It's not the same thing as changing the speed. So, for example, in a body that doesn't have mass, like light, which is problem 15, if you doubled the momentum, the speed doesn't change at all. Okay, so For massive bodies, you have that relationship that the momentum is that the velocity is proportional to the momentum. But for something like light, which has an analogous kind of thing called momentum and kinetic energy, the kinetic energy is simply proportional to the momentum, and the speed is constant. So you see the distinction there? If you're thinking more broadly, they're not the same. And it's only the same because we're dealing specifically with a massive body. Yeah. So you need to try to retain in your mind the distinction between the cause and the effect. Even though if you increase the cause, the effect increases, but that doesn't mean that the cause and the effect are the same. Okay. It's an important point. It may take a while for it to sink in, but it's an important point.
We're just basically separating one part of it from the other.
Yeah. Because mass and speed and momentum are not the same things, right? They're separate from each other. Speed is the evidence of momentum, but it is not momentum. So they are not the same thing. Now they're related to each other in a massive body, but generally speaking, they're not related to each other. Like in light, momentum and speed are not related to each other. The speed of light is the same independent of the momentum. So it may be that if you keep in mind that these things are of their nature separate things. One is an effect because it's a rate of change. One is a cause, it's a property that causes locomotion, and the other is a resistance. These things are interconnected, but they're not. Just because in the case of a massive object, one is proportional to the other doesn't mean they're the same. That's an important difference. Was there another question?
Well, with I didn't fully understand number 26, to be honest.
26 is the object moving in a circular orbit.
I'm sure it's something I should be able to understand.
Okay. So let's diagram the forces again. And we have a body moving in a circular orbit. What is the direction of the force required to keep a body moving in a circular orbit? You don't really need to know much more about it other than that there is required one. If there were no force acting on this body, how would it move?
In a straight line.
Yeah, it would go just a straight line, and if it somehow you got it. So if you were to try to make something move in a circular orbit, say a bucket of sand, in which direction would the force have to apply to get the bucket moving in a circle? Inward. You have to pull the bucket to keep it moving in a circular orbit. The force is inward. We haven't actually analyzed what is the magnitude of that force for simple circular motion yet. That's coming. We'll do that. But you can reason quite clearly that the force has to be in that direction. If you think about it, the impetus is directed tangentially to the circle. And the momentum has to keep changing in direction only, because the speed is not changing. The momentum is not changing in magnitude, but it is changing in direction. And so the force is perpendicular to the momentum. Okay? Now, let's suppose after a short time it moves a little distance. And so in that case, after a very small time, the displacement dx is tangential to the circle. Right? So what is f dot dx in that case? 0. If f is radially inward and the motion is along the perimeter of the circle, it's tangential to the circle. Therefore, the force will always be perpendicular to the motion. And so what is the work done by a force in keeping the object moving in a circular orbit? It's always 0. So what does that say about the kinetic energy of an object in circular motion? It's constant. By the work energy theorem, f dot dx is always 0, so dk, the change in kinetic energy, is 0. So the kinetic energy is not changing. Now the momentum is changing, but only the direction of the momentum is changing, not its magnitude. Yes, sir.
If I said that work equals 0 because there's no change in kinetic energy, like I said, that kinetic energy is a scalar, so if all you're changing is direction, your kinetic energy is not changing, and then I use that to deduce that work is 0, then
Well, it's not starting with the work, so you're working backwards from the work energy theorem, and so if you stated it that way,
would that be wrong?
no, I don't think it's wrong. I guess I'm all right with that. If you worked it backwards from the work energy theorem, that's kind of interesting. So, yeah, that's not bad. It's not bad. Mr. Kelly.
Is there a significance in the cross product of those two?
The cross product of the force and displacement, no, not insofar. Well, we'll come to that when we do rotation.
Do what?
Cross products when we do rotation.
Oh, rotation.
Yeah, so you'll understand the significance of cross products when we do rotations, and then various cross products come to play. Okay, so now let's see, 26 and 27. Yeah. Okay, and 27 was back to the pulley, which you analyzed in terms of forces in a previous homework assignment. Now you're analyzing the work done for a double pulley. So it has this set up. Well, there's not a second mass. It's just being pulled down with some tension on the rope like that. Okay. And so in this case, you analyze the forces required in order to lift the block. That the tension here, the minimum amount of tension in order to start lifting the block was half of the weight. So this has to be 1/2 of the weight in order to be a minimum amount of tension in order to get acceleration off, in order to lift it, just to balance the force of gravity here. And that's because the tension exists on both sides of the pulley and has to balance the force of gravity here, and so therefore the minimum tension to keep this thing from falling has to be half of the weight. Okay, but now if you work out the work done by the agent that's pulling on the rope, how much work is done, and does that change? Let's see, compared to a single pulley. So in this case, this tension must be equal to m2g in order to keep this thing from falling. And now if you displace this mass a distance h in both cases, what is the work done in the two cases? The work is the same, even though the force is half as much in the case on the left. You have to move the rope a distance twice as far because the body that's suspended has to move the same distance in the two cases. So if I'm going to move this a distance h here and this a distance h, then the work done on the end of the rope will be m2gh in this case. In this case, because the end of the rope is moving down an h, but in this case, the end of the rope must move 2h. And so the work done in this case is m2g02 times 2h. So the work is the same in both cases. So it makes the work easier because you don't have to exert as much force, but the overall work, as defined with our definition of work, it's the same either way. Okay. And let's see. Okay, any questions about the worksheet on work? Again, diagram the forces. And Okay, something to keep in mind here. Let's go back, and this is important to keep in mind. So there were two expressions for the work. That he used in the book. What is the significance of these two different expressions for the work? What is the meaning of each one? Yes, ma'am.
Is one the change in work over time?
So
The
there.
second one, because it's delta work.
Right.
Not be the work initially and finally.
Right. So delta W is clearly a change in work. So time is not explicitly in here, so it doesn't when you say overtime, but it's an amount of work done from here to here. But what is the DW? Isn't that also a change in work?
The derivative.
Yeah, it's not a derivative exactly. Yes, sir, Mr. Flanagan.
Top one is instantaneous.
Infinitesimal. Yeah.
What?
Infinitesimal. So when we were developing a calculus, we used delta x to represent a difference in x, a change in x, or a difference in x from one place to the other. And a dx represents the limit of delta x getting really small. So that's what is meant by an infinitesimal. It's arbitrarily small. So the upward expression corresponds to the work, the incremental infinitesimal amount of work that's done if I allow the block, or the mass of the body, to move a very small distance, very small displacement, dx. Okay, so dx here is a vector. It's some direction is specified, right? But it has infinitesimal length, very small displacement, infinitesimal length, arbitrarily small length. So dW is arbitrarily small. Okay. So the lower equation has to do with a finite displacement. That is, if I go 1 meter, then we're talking about the lower expression. So this is a finite displacement. Now, why would I be concerned about the difference between these two? Any thoughts about that? Why do I have two different expressions? Yes, sir, Mr. Trimble.
Because you only need the bottom if you're working with two actual numbers.
Let's try again. Mr. Flanagan.
The infinitesimal might change with each increment.
What changes with each increment?
The values.
Values of?
Work and distance.
Yeah, not work or distance, but yeah. What are the forces changing? Then I have to deal with infinitesimals. This expression is the work done by a constant force, that is a force that doesn't depend on x. So this expression, the latter expression, is not as general. This is for a special case. F does not change over the displacement. So the upper expression is the beginning of a more general expression. How would I calculate the work done if the force is changing? Well, let's think of some cases here. We haven't dealt with forces that change, right? Not much. Gravity, does the force depend on if it's here or down here or over here? The force of gravity is a changing. It's the same. If it's a block on an incline and it's sliding, there's the normal force, there may be a tension, there's maybe friction, there's gravity, or any of those forces changing. As long as it continues to slide, none of them are changing. Now if it stops and goes back the other direction, now the kinetic friction has changed, swapped directions. So there's an example where force has changed. We're going to, in the next chapter, consider springs. An example of a spring. So if you have a spring, let's hang a mass from the ceiling like this, and let's pull down. The more I pull, the farther I stretch the spring, the more the spring pulls back. Now the force is proportional to the stretch of the spring, and it will change with distance then, change with displacement. The more I displace it, the bigger the force is. So we won't get into a case until the next chapter, when we're going to have to go back and consider this more general situation, this case. This is the general case. This applies for all forces. The work done by a force that's changing with location. And in that case, we're going to have to get the total work done by adding up little incremental pieces of work. That's an integral, and we haven't done an integral yet. Okay, so that's why I haven't taken you to the next step. This first step is building up to doing an integral, and we're not going to really do integrals until we get to the next semester. Okay, so for the present, realize that this is a special case. This is true only if the force is unchanging over the displacement. If the force changes with displacement, we have to calculate the work another way. This is not going to work. Calculate the work this way. Okay. And in all of these cases that you were doing in the worksheet on work, they were always forces that did not change with displacement. And all of the examples we'll be doing in this chapter are like that. When we get to the next chapter, it will be changing with location. Okay, so for Friday, you have two cases, two worksheets to do on kinetic friction and static friction. I believe that's right. Is there anything else?